I'm going to talk about the most important algorithm in the 20th century, which is invented by Coley and Tukey. Why it is the most important algorithm? Because you can see in many applications such as radar, sonar, communications, and machine learning, everywhere you can see fast Fourier transform. And let's see why it is so famous and it's so widespread in many applications. What is FFT? FFT stands for Fast Fourier Transform. Practically, how we can compute Fourier transform? We use DFT. Previously, I talked about DFT, discrete time Fourier transform, and it was a summation xk equals to n from 0 to n minus 1 xn e minus j do pn k n for k equals to 0, 1, n minus 1. We want to compute this. How many operations that I have to do to find DFT samples? As you see, for each point of this summation, you need n complex multiplication and n minus addition, complex addition. And you have n point, so you need n squared complex multiplications and n multiplies by n minus 1 multiplex addition. I say it needs approximately order n squared operations. We need, for computation of this summation, we need this. Actually, this is the cost of this kind of computation. But FFT algorithms, actually there are a family of algorithms. They can give us order of n log n base to 2. This is the computational complexity of FFT algorithm. Let's have an example and see what is the difference between these computation complexity. For example, we want to compute n 1024 point DFT. If we directly compute DFT based on this summation, we need n squared, approximately 10 power of 6, 1 million operations. What about DFT? And actually it's 2 power of 10. Then we have n log n base to 2 is approximately 1000 multiplied by 10, it's 10,000. Here 10,000 operation. Here 1 million operation. 100 times we reduce the operation. That's why FFT algorithm is computationally efficient, and you can see in many applications, radar, sonar communications, for example, OFDM in wireless communications. You can use FFT in radar, Doppler bang and range Doppler analysis can use FFT everywhere. Everywhere you can see FFT. Let's dive into Fast Fourier Transform and see how it works. As I said, there are many algorithms for FFT. Two well-known of these algorithms are Decimation-In-Time, other Decimation-In-Frequency. And in this video, I'm going to talk about Decimation-In-Time FFT algorithm. And I consider n equals to 2 power of, for example, nu, which I call it radix 2 algorithm. Because in every stage I divide n over 2. And it's so simple. In every stage I decompose samples in even and odd samples and try to compute DFT successively until reach to the 2-point DFT. Let's see how it works. We are gonna compute this summation. First of all, I use this symbol WN, KN. WN defined as a complex number e minus j 2 pi over n. We use symbol WN to power KN. And I now decompose. Decimation is decreasing the samples. Decimation by 2, it means, for example, we get even numbers and remove odd numbers and vice versa. So I can break this summation into a smaller summation. N even samples plus n odd samples xn wn kn. N odd, it means I can write x2r even numbers. wn k2r, r from 0 n over 2 minus 1 plus n odd, it means I can write x2r plus 1 wn k2r plus 1 r from 0 n over 2 minus 1. Here I can decompose it to wn k2r multiplied by wn k. And I can continue r equals 0 to n over 2 minus 1. Here I can rewrite this wn power of k2r. I can write it wn over 2 kr. What is this? This is n over 2 point DFT plus summation is on r. I can get wnk out of summation. wnk r from 0 to n over 2 minus x to r plus 1 w n over 2 k r. This is also n over 2 point DFT. This is also n over 2 point DFT. What I did, an n point DFT can be computed by linear combination of two n over 2 point DFTs. By doing this, how I reduce the computation? Let's compute the computational complexity. For n over 2 DFT, we had n over 2 squared operations. We have 2 here, and so 2 multiplies by this term, and we have n multiplication for combination and also addition, so we add n to this term, which is n squared over 2 plus n. If n greater than 2 and if n is large enough, then we want to easily see this number is lower than n squared. Approximately, for example, it's somehow the computation decreased by the number of 2 if we neglect n in front of n squared over 2. But the algorithm doesn't stop here. We continue. For example, this n over 2 point DFT, we can decompose it to n over 4 DFT. I will do this process until we reach 2 point DFT. Let's compute a 2 point DFT. For example, xk equals to n minus 0, 1, w2, kn. Here is also xn for k equals to 0 and 1. So x0 equals to x0 plus x1, and x1 equals to x0 plus w2 power of 1 x1. And if I have x0, x1, I can write this graph, x0 plus x1, and also x0 plus here w2, 1. I can write it w2, 1, w n power of n over 2. They are the same. And this is x0, this is x1, and here also I can write wn0. This structure, we call this structure butterfly. and we can see FFT algorithms form from the butterflies. In every stage we have butterflies. So how many stages that we will have when we are decomposing n until reach to 10? For example, for n equals to 8, we decompose to 2n equals to 4, and then we decompose n4 to n equals to 2. There are 3 stages. So if generally we have n point DFT, how many stages does I need to reach to 2? Simply log n to base 2. And in every stage we have n complex operations. So the total number of operations for FFT algorithm is n log n to base 2. This is the computational complexity of FFT algorithm. Let's continue and see some figure to understand deeply. In the first figure, you can see we divide our sample. This is for n equals to 8. In the first stage, decimation is made by factor 2, so data or samples is divided to even samples and odd samples. 0, 2, 4, 6, 1, 3, 5, 7. This is decimation by 2. Even and odd samples. And we have n over 2 point DFT, and then we will have a combination. We implement this formula. We call this term GK and this term HK. And for n over 2 point DFT, we know that GK equals to GK plus n over 2. DFT is periodic. And HK equals to HK plus n over 2. So, for example, x0 is g0 plus h0 multiplies by wn0. x1 is g1. It means xk equals to gk plus wnk hk. x0, x1, 2, 3, 4, for example, x5. x5 is g5, but g5, we don't have g5. We use g1 because it is periodic, so we bring g1 here. wn power of 5, gn5, h5. We don't have h5, we use h1 for x5. And we do the same for other DFT samples. As you see, we have 2n over 2 point DFT, and the output combine to build n point FFT, 8 point FFT. If we want to continue, we want to decompose this. This is 4 point DFT. I can decompose it in 2 point DFT. Again, even and odd number. Here, even is this, x0, x4. Odd is x2, x6. We do this process for 2 blocks. Let's see. We have 4n over 4 point DFT, x0, x4, x2, x. Then the output will be combined to form 4-point DFT. Here also we use 2-point DFT to form 4-point DFT. And then the 4-point DFT are combined to form 8-point DFTs. Finally, if I put butterflies instead of 2-point DFT, we can see the signal flow graph of whole n-point FFT algorithm reduced to decimation in time. How many stages do I have? 1 stage, 2 stage, 3 stage, log n to base 2. How many multiplication in each stage? 1, 2, 3, 4, and continue to 8. N multiplication in every stage, n multiplication that I have. How many addition? These are additions. These are additions. In each stage I have n additions. So the number of operations in n log n to base 2. There are 2 points that I have to say. First, you see butterflies, and the structure is formed from the butterflies. And in every stage, butterflies get bigger. For example, we have a butterfly here, then we see a butterfly, it's bigger and bigger. In every stage, butterflies get bigger and get bigger. So structures uses butterflies. And another point, actually the last point here, is the order of the input. Actually, if we have a memory with the, for example, order of 0, 1, 2, 3, 4 until 7, if I can use the binary form of these numbers, for example, x0, x1, x2, I only need do bit reversal. We use bit reversal to find how data should be in the input of our signal flow graph. For example, here bit reversal doesn't affect, so we have x0. This is for signal in time domain. And here bit reversal, it means x1 0 0, x1 0 0 means x4. So here we have x0. Bit reversal doesn't affect here x0 1 0 is x2, or for example x0 1 1 it will be in time reverse, in bit reverse x is x1 1 0, it is x6. So for ordering of the input, how data fit to the algorithm, we use bit reversal. If we use the binary address of the memory, then by using bit reversal we can have the order of data at the input of signal flow graph. We reached to the end of this video. I hope you enjoy it. Please support my channel and subscribe my channel to see more videos regarding signal processing.